All right, so centroids are used, they're called a shape property. So they're used, we use these when we, in different applications. We use them when we design beams. We also use them when we pick stuff up, like picking up that slab there. You got to know where the centroid is to get that thing to balance. Okay. So let's have a look at how we would find these. So the centroid, the word comes from the word center. It's the center of an object. Okay, so often we will apply the force of an entire object at its centroid. We've been doing that with the center of gravity already, is what we've been doing. Let's see how we could find these. Okay, now here's how we do this. Let's kind of look at the idea of resultance here. And let's kind of use that idea to figure out this formula we use for centroids. All right, so I've got some weights there. I got 1, 2, 3, 4 of them. I can add up all the weights and I can get 240 newtons. That's the net weight acting down. Now let's figure out where we could put this 240 newtons. How far over could we put it? Where's the one place we could put that total force? Well, we're going to have to do a weighted average is what we're going to have to do because there's different weights. So we're going to have to do a weighted average of the distances. That's how this is going to go. All right. So the net force is the sum of the four forces. It's negative 240. I could take the moment about the origin. I'll call the origin A. So I go sum of MA, 50 newtons times 0.02 meters. Now notice what I'm doing here. I'm going to use the left-hand rule on this because I don't want a bunch of negative signs in that. I'm just going to call that positive, okay? That's legal as long as you call it out, okay? The right-hand rule is somewhat arbitrary. Okay, so I'm calling clockwise positive. That's what I decided to do on this, just so I don't have a bunch of negative signs in here. All right, so the sum of moments will be 50 newtons times 0.02 meters. 90 newtons, 2 and 3 makes 5, so that's 0.05 meters. 60 newtons times 2, 3, and 1, 0.06 meters. And 40 newtons times 2, 3, 1, and 2 makes 8 centimeters, 0.08 meters. So if I add up all those moments, I get 12.3 Newton meters. Now that's clockwise. Okay, I'm kind of using a funny sign convention here. So if I want to know where this 240 newtons could be said to act, do you remember what we did? How do we figure out how far over from here that 240 newtons would be? What's our little trick for doing that? What do we do with our 12.3 Newton meters? What's that now? We're after meters. Yeah. Divide by, the resultant force, see? There we go. Okay, that's how you could do that.
You mean divide by 240?
Yeah, I do.
Okay.
Which I didn't write down. So why don't I write that down? Yeah, thank you. All right. Now, another thing I'll mention to you is I used to tutor physics, and I didn't know much about physics, but I knew that units had to work out. I tutored an awful lot of physics just knowing that units would work out. It was amazing how well that worked out sometimes, okay? So I'll divide that out, and that will get me the distance. Remember doing this? Okay, so, and I get 0.0513 meters, that's 5.13 centimeters. So that 240 is going to hang right about there, okay? That's where that's going to be. Another way to think about this, if you want to think about it not so much in these technical kind of terms, resultants and stuff like that, if I've got a balance beam, where am I going to put the fulcrum to make that thing balance? If I'm going to hang those weights off a beam, where does the fulcrum go? Do you think? Yeah, I think so. Okay. So that's another way to be looking at that. I could put a balance beam there if those weights are hanging on wires. I would put the fulcrum, the balance point, at where that 5.13 centimeters over, okay? That is the center of that system. You okay with that? It's just another way to explain centroid, okay? I don't know if you've had this before, okay, or not. Maybe you've had it in Math 252 when you sum things up. Maybe you've had it in physics. I don't know, who knows where you've run into this before, okay? So we can generalize this, okay? Our X bar, as we call it, is 5.13 centimeters. Okay, that's X bar, our X centroid. That's the balance point of that system. So the general form of this, what we just did is we just did that. We summed up on the top each individual weight, which I'm representing with a small w, times its distance from the axis, which I'm calling x with a squiggly bar on it, so kind of a small x bar, and then we divided it by the total weight, and that got us the large x bar, which we are calling center of gravity. Okay. Now you can have centers of a lot of stuff, okay? You can have center of mass, you can have center of volume, and you can have the center of an area called an area centroid. It's the same form of that equation. So the x bar for a centroid is the sum of we break the object up into little areas, okay? And then you multiply each little area by its x bar distance from some set axis, and then you divide that by the total area. It's the same formula that we just used. We're just using area instead of weight. It's the same idea, okay? So that's the centroid formula for an area, which you'd use like if you had a plate of metal or something like that, okay? Or the cross-section of a beam, if you want to know where the centroid's at. All right, so that's one version of that formula. So x bar is sum of x bar a, little a, over the total area. Now that's breaking the object up into discrete pieces that you can measure and look at. If you have a composite beam of something, you could, or like that, you could break it up into all the pieces that make it up. So for instance, that T-beam there, I could break that up into a trapezoid for the stem of the T-beam right there. And then I could break it up into the rectangle on top of the T-beam. I could do that, and I could find its centroid, okay? And that works fine for a lot of the stuff that we do when we're working. Now, of course, sometimes we have curvy kind of areas with functional curves. And what we got to do then is break it up into a bunch of really small pieces, okay? And we call DAs, all right? And we measure the centroids to each one of those little DAs. And there's so many of those things that this thing actually we have to work really fast. So that thing starts to accelerate, and when that accelerates, that thing starts to deform into something that looks more like that, right? And kind of let acceleration on there. And what we get is x dA over A, right? Okay, so that's another way to do that. So the method you choose kind of depends on the problem you've got. If I've got a problem that looks like this with a couple of kind of functional curves on it, I'm probably going to have to integrate it, because what integrals are is what? Breaking something up into a bunch of little pieces and adding them up. That's really what an integral is. Okay. Now if I've got a different kind of shape, maybe that looks like that, then I'm going to use the sum method, okay? So you pick the method to match the problem you've got. I wouldn't try and run an integral to do that. It would be, you could do it, but it'd be a bit of a, way too much work, and yeah.
That's a vertical line test.
Yeah, it doesn't, vertical line test. Okay, but I wouldn't try and do this by summing. I would have to integrate to do that. So it just kind of depends on what you're dealing with as far as the method you're going to use goes. All right. So why don't we take this? Why don't you draw this up real quick? I don't think I've got this in your book. I don't think. right, so if I'm going to do this, what I'm going to do is I'm going to break this thing up into pieces. Okay, now you'll have something like this on the final probably. So please, there is a method to this, all right? And so I would like you to kind of take your time and employ the method. Again, make it visual. Draw the centroids in there. Put them about in the right spot. Make the sketch to about the right scale. Okay. Then draw in the X and Y bar distances. That way you get a check on your work. You can say, is that looking about right? Is it not looking right? What's going on here? So this is a little bit like those moment problems where I was saying, get everything figured out first, then plug it in. It's a similar deal with this. Okay. So once I've got that, I'm going to want areas. What units did I use there? Okay, so there you go. So I'll start with that, and then I'll get the areas. The top area is 2 by 2. It's 4 centimeters squared. I'm going to stay in centimeters on this. The bottom one is 8 by 4, which is 32 centimeters squared. Then I want those distances. Now the important thing with the distances is they all measure out from the same set of axes. So I want to start with my X and Y axes there and measure to those centroids. Okay. So what? This is 8 here, right? So I'm pretty sure that that's 4. And that is 6 and 2. So I'm pretty sure that's going to be what? 7? Which is 6 plus 2 over 2. And so I get to that centroid. And this one here ought to be about 2, which is half of 4. And 4 plus half of 2 ought to get me about 5 there, which is 4 plus 2 over 2. Okay? So I'm going to get those distances figured out. And I'm just going to get everything on a sketch and good to go. Yeah, there's lots of ways to do these. You can break them up any which way, as long as they make sense. You can even use cutouts if you want, whatever. Okay. So now once I got that all sketched up, then I just combine everything into an equation. That's how I would like to do these. We all good with that? I think I've got, yeah, there we go. So X bar, the 32 centimeters squared will be by 4 centimeters. And the 4 centimeters squared will be by 7. So I multiply area times distance, and I divide by the total area, which is 36. That's for X bar, and that comes out to be 4.33. And then for Y bar, what I'm doing is I'm going 32 times 2 for the lower one and 4 times 5 for the upper one. Divide that by 36, and I get 2.33. So I'm getting something on the order of right about there is what I'm getting for this final centroid. And then I kind of ask myself, well, okay, if that's a plate and I turn that upside down or sideways and try and balance it on a pencil, will it balance there? That looks about right, you know.
Can you go over where you got all your numbers?
Okay, I'm getting the areas. Okay, and the areas for the upper corner is 4, and the big rectangle down on the lower left is 32.
Yeah, got that.
And then
you did 32 times 4,
okay,
which is the top side of that centroid.
the 4 is from the y-axis to the centroid of the 32. It's half of 8.
Okay.
And then this one is 7. The 4 is times 7 because I'm going.
That's X, sorry.
Yeah, I'm doing X and then I'm doing Y. Right. I gotta do this separately. Kind of like vectors in a way.
I was trying to do it all at once.
Ah, okay. Wasn't working. Okay, so that's a little run on that. We'll get into this more on Wednesday. So I got a few of these frames and machines. Now these will be due Monday because we got our test coming up on Friday. So these are due Monday, which would be, I think, the 9th. Is that right? And what are these? There's going to be a few of these. So 321 and 2 and 3, 321, 322, 323, and then a couple more. then 325
This
and
should be the
6.
next homework is due, right?
Yes, I believe so. Yeah, 325, 326. Okay, so those are due Monday, the 9th. Okay, we'll go over review for the test. I'll cover these problems a bit too on Wednesday. Okay.